Hi, everybody. In this series of videos, we are going to walk through a few important and foundational components of system design. This video is really a preview of the next few videos where we're going to walk through some foundational pieces of system design. While they may not appear exactly as they are in interviews, they form the foundations of many interview questions. For example, Unique ID Generator is a critical component of designing TinyURL, while the CAP theorem applies to pretty much all system design problems where scalability and consistency matter. We are going to walk through every one of them and actually many more in the next few videos. Stay tuned.
Okay, this is the first video of the series. We're going to design a unique ID generator. In distributed systems, such design is crucial to ensure that each ID is globally unique and efficiently generated. Depending on specific requirements and environments, there are various strategies for generating unique IDs. Below, we will walk through several common methods, their implementation details, advantages and disadvantages, as well as applicable scenarios. A UUID is a 128-bit identifier widely used in distributed systems. UUIDs have 5 different versions, and version 4, UUID v4, is the most common one. A UUID consists of a version number, a variant field, a random number, and possibly a timestamp, clock sequence, and a node. Note that UUID v4 relies entirely on random numbers. The advantages are: first, it does not rely on a centralized server, making it suitable for multi-node systems. Second, the 128-bit length ensures that randomly generated UUIDs are highly unlikely to collide. Third, UUID generation is purely local computation, which makes it highly efficient. While the disadvantages are: first, UUIDs are randomly generated, so they cannot be arranged in chronological order. Second, UUIDs are 128 bits long, which increases storage and transmission costs. Database autoincrement ID is a classic method for generating unique IDs, and many relational databases have built-in auto_increment functionality. Here is an example SQL statement. Whenever a new record is inserted, the database automatically generates an increment ID. The advantages are: there is no need for additional ID generation logic. Auto-increment IDs are sequential, easy to sort and manage chronologically. The database ensures the uniqueness of IDs. While the disadvantages are: when multiple machines are writing simultaneously, relying on a central database can become a performance bottleneck, and if the database becomes unavailable, the entire system's ID generation will be interrupted. Snowflake is an efficient distributed unique ID generation solution developed by Twitter. The IDs it generates are 64-bit long integers, consisting of a timestamp, data center ID, machine ID, and a sequence number. Note that the sequence number is generated within the same millisecond to prevent ID duplication. The advantages are: first, each node can independently generate IDs without central coordination. Second, IDs are generated locally on each node, with no need for network requests. Third, IDs are based on timestamps, so they possess a certain level of ordering. The disadvantages are: if the machine's clock is rolled back, it may cause ID conflicts. Redis is a high-performance in-memory database, and its INCR command can be used to generate incrementing unique IDs. Since Redis is single-threaded, each INCR operation is atomic, so there is no need to worry about concurrency issues. The advantages are: Redis operations are very fast, making it particularly suitable for high concurrency scenarios, and there's no need for complex generation logic. While the disadvantages are: all nodes depend on the same Redis instance. If Redis becomes unavailable, ID generation will be interrupted, and it may still become a bottleneck. Segment mode is an optimization strategy for generating distributed unique IDs. The main idea is to allocate a range of continuous IDs to each service node by a central server. Each node retrieves a continuous range of ID numbers. When the node needs to generate an ID, it takes a value from the allocated range. Once the range is exhausted, the node requests a new range. The advantages are: first, the central service is only responsible for allocating ranges, minimizing frequent network interactions, and second, the generated IDs are continuous, providing good ordering. Third, service nodes generate IDs locally, resulting in almost no delay. While the disadvantages are: additional logic is required to manage the allocation and usage of ID ranges, and if the central service becomes unavailable, new ranges cannot be allocated, leading to interruptions in ID generation. Thanks for watching. For more information, please visit bowsier.com. Consistent hashing is a commonly used hashing algorithm in distributed systems, primarily used to distribute data evenly across multiple storage nodes, reducing the overhead of data redistribution when nodes change. It is widely used in distributed caching, load balancing, and distributed storage systems. Below is a detailed explanation of its working principle, workflow, and a few examples to illustrate its application. In consistent hashing, both data and nodes are mapped to a virtual hash ring. First, each storage node in the system is mapped to a position on the hash ring using a hash function, such as SHA-1, based on its ID. Next, each piece of data that needs to be stored, i.e., the key in a key value pair, is also mapped to a position on the hash ring using the same hash function. A data item will be stored on the first node in a clockwise direction whose hash value is greater than or equal to that of the data item. If the data item's hash value is larger than all the node's hash values, it will be stored on the first node, looping back to the beginning of the ring. Assume there are 3 nodes, A, B, and C, which are mapped to positions 100, 200, and 300 on the hash ring. Now we have some new data to store, with hash values of 110, 210, and 350. The workflow is as follows. Key 1 has a hash value of 110, so the next node in the clockwise direction is B200. Thus, Key 1 is stored on node B. Key 2 has a hash value of 210, so it will be stored on node C. Key 3 has a hash value of 350, which wraps around to node A, since it moves clockwise past C back to A. A key advantage of consistent hashing is reduced data migration. When nodes are added to or removed from the system, only a portion of the data needs to be reassigned. Let's say a new node D, with a hash value of 250, is added after the existing nodes A, B, and C. In this case, some data originally assigned to node C will be reassigned. Key 2, hash value 210, which originally belonged to C, will move to D because D's hash value is greater than 210 but less than C's, while all other data remains unaffected. Now for node deletion, if node B, with a hash value of 200, is removed, data originally assigned to B will be reassigned to the next node in the clockwise direction, which is C. In this case, Key 1, hash value 110, will now be stored on C, minimizing overall data reassignment. To further address the issue of load imbalance, consistent hashing introduces the concept of virtual nodes. Virtual nodes are multiple replicas of physical nodes, created by hashing the physical node IDs multiple times and mapping them to different positions on the hash ring. This approach allows each physical node to have multiple virtual nodes, resulting in a more even distribution of data and preventing any single node from becoming overloaded due to uneven hash distribution. For example, suppose there are 2 physical nodes, A and B. Using the virtual node technique, A and B can have virtual nodes A1, A2, A3, and B1, B2, B3, respectively, mapped to multiple positions on the hash ring. This means that even with a small number of physical nodes, the data can be more evenly distributed across the various virtual nodes. When using consistent hashing, there can be instances where certain key value pairs become overly concentrated, resulting in excessive access pressure on a specific node, referred to as the hotspot problem. To address the hotspot issue, several methods are commonly employed. Chardin split large datasets into smaller segments distributed across different nodes. Replication mechanism. Create multiple replicas of hot data and distribute them across different nodes to reduce the pressure on a single node. Load balancing. Continuously monitor the load on each node and dynamically adjust the distribution of requests. Thanks for watching. For more system design lectures and much more tech interview materials, please go to bowsy8.com. A key-value store is a simple and efficient data storage model that stores data in the form of key-value pairs. The key identifies each data item, while the value contains the content of that data item. Due to its straightforward design and high lookup performance, key-value stores are widely used in caching systems, configuration management, session storage, and other areas. Next, I will introduce how to design a simple key-value store in detail, discussing its storage structure, lookup methods, scalability, and data consistency guarantees. The core idea of a key-value store is to quickly locate a corresponding value using a key. Although this concept is simple and intuitive, real-world applications often require considerations such as data growth, scalability in distributed systems, persistent storage, and concurrent access. Key design aspects are storage structure, how to store key-value pairs, query performance, ensuring efficient lookups even with massive data volumes, persistent storage, methods for writing data to disk or other persistent storage, distributed scalability, supporting large-scale distributed clusters to ensure scalability and high availability, data consistency, maintaining data consistency across multiple nodes in distributed systems. Concurrent access, ensuring data consistency and thread safety in high concurrency environments. The simplest key-value store can directly use a hash table, hash map, as the underlying data storage structure. Hash tables have a lookup complexity of 1, making them ideal for quickly finding values based on keys. However, when data volume becomes very large, a single machine's memory may not be sufficient to hold all data, and distributed storage mechanisms are required. In some persistent storage systems, such as databases, AB+tree can be used to store key-value pairs. AB+tree is a self-balancing tree structure suited for range lookup operations and can effectively reduce the number of disk I/O operations. It's suitable for large-scale data storage and supports range queries, while compared to hash tables, B+trees have higher lookup complexity, O log n. A distributed key-value store relies heavily on the concept of consistent hashing to achieve consistency. This is what we discussed in the last lecture. Key-value stores often adopt an eventual consistency model. Although different nodes may hold inconsistent values at any given moment, all replicas will converge to a consistent state over time. This model is suitable for scenarios requiring high availability, where a certain degree of strong consistency is sacrificed. To maintain data consistency in distributed systems, many key-value store implementations use a quorum mechanism. When performing a write operation, a majority, e.g. n/2+1, of replicas must successfully write the data for the operation to be considered successful. Similarly, read operations require reading from a majority of replicas to ensure that the most recent data is retrieved. Thanks for watching. That's it for today. We are going to continue the discussion of key-value store in the next video. For more system design questions and even more tech interview materials, please visit bowsy8.com. Okay, this is part 2 of the lecture for key-value store. In part 1, we talked about the design principles, storage structure, and consistent hashing. In this video, we will discuss more scalability perspectives of key-value store. Key-value stores typically use memory as the main storage medium to enhance access speed. However, since memory is volatile, a reliable persistence mechanism is essential to save data to disk and prevent data loss. A common persistence method is write-ahead logging, WL. When a write operation occurs, it is first logged to disk, then the data is written into memory. In the event of a system crash, data can be recovered by replaying the log. In addition to WL, key-value stores can use periodic snapshots for persistence. During operation, the system periodically saves the current in-memory data state as a snapshot file in the background. If a crash occurs, the system can be restored by loading the latest snapshot and replaying the log. In high concurrency environments, key-value stores need to handle multiple concurrent operations and prevent race conditions. We can use two locking mechanisms. Optimistic locking addresses concurrency issues by tracking data version numbers. When an update is performed, the system first checks if the version number matches. If it doesn't, it means the data was modified by another operation, requiring a retry or failure. This method is ideal for read-heavy scenarios. Pessimistic locking prevents other concurrent operations from accessing data by locking it until the current operation completes and releases the lock. This approach suits write-heavy scenarios, but can lead to higher performance costs. A hot key refers to a key that is accessed frequently, causing heavy load on the storage node holding it and impacting overall system performance. In distributed key-value stores, solving hotkey issues is especially important, as certain data is accessed far more often than others. A few solutions are key sharding. The value associated with a hotkey can be divided into multiple fragments, each stored on a different node. This balances the load and prevents a single node from overloading due to the hotkey. Replication. Creating multiple replicas of hot data disperses request load. Replication allows multiple nodes to store the hot data simultaneously, enabling clients to randomly select one node to read data from, thereby reducing the load on the node holding the hotkey. Caching. Hot data can be cached in memory to reduce pressure on the primary storage. Dynamic load balancing. Can monitor each node's load status, redirecting part of the request to lower load nodes if a node is overloaded due to a hotkey. Request coalescing. When many clients simultaneously request the same hotkey, the system can merge these requests, combining multiple identical requests into one operation, thereby reducing the load on storage nodes. Thanks for watching. For more system design lectures and much more tech interview materials, please go to bowsy8.com.